Hello everyone, my name is Eric Tanner, and today we're going to be discussing a research paper that is titled Model-Based Diagnosis in Fault-Tolerant Control for Ensuring Torque Functional Safety of Pedal-by-Wire Systems. And essentially, the goal of this paper is to develop models and simulations to detect and have fault control within a system, uh, particularly in this one a pedal-by-wire system for like a gas pedal or brake pedal on a car. Um, they're using ISO 26262 standard for a guideline and develop some of these models and how to classify the risk associated with each fault that could occur. So we'll dive into this and we'll discuss some of these details as we go through this research. As an overview here of the topics we'll discuss, first we'll take a little look at ISO 26262 standard. We'll touch on some model-based functional safety, look into fault-tolerant control systems, and fault detection isolation systems. We'll look at an implementation example, which is a pedal-by-wire torque functional safety system for an electronic vehicle. The basic principles for this example can be applied to any powertrain type. Electric vehicle is just chosen here as an example, but this could also be applied to a gas engine as well, or gas vehicle. Uh, we'll also look into some solutions for some fault-tolerant control strategies, and also there's some simulation results and analysis of this research, so we will also cover some of that in detail. I just wanted to go over a couple of highlights about the ISO 26262 standard. This was already discussed in good detail by Dr. Ray, but I just wanted to bring everybody back into what we're discussing and talk about how it applies to this research. It was a functional safety standard for the automotive industry. It was an adaptation of the IEC 61508 standard. It talks about life cycle for a system and the requirements that that system should have for its design and implementation phases. Uh, the standard itself is a risk-based standard, and this is referred to as automotive safety integrity levels. They are also referred to as ASILs. The ASIL levels that we're going to discuss, they're an A through D rating, but there is also a quality management rating as well. The ASIL A is the lowest amount of requirements, whereas ASIL D is the highest amount of requirements for that particular system. And this additional rating, which is ASIL QM, or quality management, this has no actions required or no requirements tied to that particular element of the system. In the ISO 26262 standard, there is mention of safety cases, and these are basically a way of looking at a safety problem and looking at the risk associated with it, how to manage the risk, and faults that could occur. Um, the management of the risk is where the fault detection isolation comes into play, which is discussed in this research, and fault tolerant control, which is also the response to the fault detection and isolation. The ISO 26262 standard discusses a life cycle model, which is referred to as the V model. This is a methodology for developing functional safety within a system. It goes through from the design phases and covers also the implementation phase of the system. This research really focuses on 5 elements of this V model. The first is defining all of your components. The second is identifying the hazards and assigning the ASIL level. The hazard analysis and risk assessment this step is referred to as PARA. The third is a simulation where you model the faults for the system and determine whether or not that ASIL level is the most accurate for the system based on the assignment from step 2. Step 4 is you're implementing the fault tolerant control system, and number 5 is the assessment of that system where you're testing and making sure that all the requirements are met for the functional safety of the system. Now that we've discussed some of the basic principles that we'll use from the ISO 26262 standard, we'll discuss the problem that this research is addressing, which is the torque functional safety problem. This is quoted as the occurrence of unintended high power accelerations starting from a stationary position or low speed accompanied by an apparent loss of braking effectiveness. The goal of this research and the problem at hand is to determine a model-based way to have a functional safety solution that can quantitatively address the faults that could occur and how to react to those faults. The models use the fault tolerant control, or FTC, to control the fault or react to a fault, but they use FDI, or fault detection and isolation, to detect the faults. These two principles paired together are used as the overall solution and create a detection and control loop themselves. So we'll go through the systematic approach, which was defined in earlier slides, and the first step was to define the components of the system. For this electric vehicle, we have a pretty simple interface here. We have a battery source, an electric motor or generator, well actually both electric motor and generator. We have a gearbox, inverter, the EM controller, which is your torque control, the wheels, pedal sensors, and the driver as the input to the system. The next step in this functional safety approach is to address the hazards, determine the hazards and the risk associated with them, and assign the ASIL classification. The factors involved with this are the SEC, or they stand for severity, exposure, and controllability. Severity, exposure, and controllability are labeled through a 0 through 3 classification, 0 being the least hazardous and 3 being the most hazardous. The severity is related to hazards to humans, where exposure is the probability of the hazard happening, and then controllability is once the hazard has happened, what is the ability of either the driver or the control system to react and control to potentially mitigate the hazard from getting worse or happening at all. So in this research, they took the torque functional safety problem and they broke everything up into each component for the system, and they discussed everything we've talked about thus far. They discussed the SEC rating, the ASIL rating, potential failure modes, consequence of the failure, and potential causes of the failure. For instance, here we'll take a look at the first item, which is the accelerator pedal. A potential mode for this to fail is when the accelerator pedal is too sensitive. The consequence for this would be that the vehicle lurches forward when you're accelerating. Here's the SEC rating for this failure, or this component. And the one thing to note here is that they mentioned that the SEC rating is a 0 through 3 base rating system, but this table went against that, it seems, and they went with a 1 through 4 rating. So for the severity of this rating, or this failure, is a severity level 2. It's not extremely severe to lunge forward, but it could be potentially dangerous. The exposure level for this is a 4 because if the accelerator pedal is too sensitive, the probability of uh, encountering this is very high because you need to use the accelerator for driving the car. And the controllability is rated as a level 2 because this is not a totally out of control scenario. It can be fixed by the driver removing their foot from the accelerator. It's not a total loss of control, so that's why they gave it a level 2. And the overall ASIL rating is a B, which is relatively low. It's the second from lowest in this rating system. So the next phase in modeling this system is to do fault modeling of the system. One of the approaches for this would be to inject faults into the system, whether it be brake pedal stiction, the accelerator pedal sensor fails, or the cruise control system has malfunctions in it. Particularly this research addresses a scenario where the accelerator sensor is stuck at 20% in an attempt to stop at a red light. So if you can imagine this, you're driving and you're trying to now stop, you would take your foot off the accelerator and put it on the brake as you're coming to a red light. So in this scenario, having a foot on the brake and the gas at the same time would normally be encountered and corrected by a brake override system. They're assuming that this system is disabled, so it wouldn't recognize that the foot is on the brake and accelerate at the same time and take the brake as higher priority. This would try to allow both to happen in this scenario. So this failure is a severity level 2, exposure level 4, and a controllability level 3. It would be considered a severity level 3 if the velocity change for the vehicle was greater than 40 kilometers an hour, but in this scenario, it's less than 40 kilometers an hour. This plot on the right I threw in this slide because it shows the result of the accelerator sensor being stuck at 20%, where the engine's trying to accelerate while you're also trying to brake. You're still able to stop the vehicle, but it's not going to stop it at the same rate at which it would with the accelerator not active. So you can see on the right that we have the blue line is the normal scenario of your time to brake versus distance, and the dotted red line is the 20% accelerator stiction level, where you would take a lot longer to stop the vehicle if the accelerator was also stuck at 20% while trying to brake. The fourth step in this phase is to implement a model simulation and fault-tolerant control. So you want to define your safety requirements and technical requirements for the system and determine, now that you have a fault detected, how are you going to control it? So for each of these models, they particularly use structural analysis for the fault detection and isolation and the fault-tolerant control. The Structural analysis is a method for determining the fault and also controlling the fault. So in this scenario, there are unknown variables, which are dynamic and algebraic states, and known variables, which are known input signals and direct output signals from sensors. Um, what it tries to do is look for redundancy in unknown variables to try to reduce the problem. The Dolmage-Mendelssohn decomposition model, I may have butchered that, but this fault detection model is a way for determining whether or not you can actually detect a fault when it occurs. The uh, definitions that are used here are three different ones. There are structurally underdetermined, which is there are fewer equations than unknown, and the structurally just determined, there's the equal number of equations and unknowns, and then the structurally overdetermined, where there is more equations to solve than there are unknowns. One of the problems with the structural analysis approach is that to detect faults, the problem has to be structurally overdetermined. And because of this, modeling a large system, you're probably not going to run into the scenario where you have more equations than unknowns. So to help with this, there are these sets referred to as minimum structurally overdetermined sets. And so it's a way to break down the entire system into smaller sets where the Dolmage-Mendelssohn decomposition of that set produces one more equation than unknown. So you're always overdetermined, but you're at the minimum level of structurally overdetermined. This helps break the problem down into smaller systems or components and allows you to detect faults. So this research used ISO 26262 as kind of a guideline to this model-based modeling and simulation of components within a car, and particularly this scenario, which was the accelerator pedal stuck at a 20% value when you're trying to brake the car. This is the solution they offer for the uh, scenario that we discussed. As I mentioned, the brake override system that they assumed was disabled, they're now offering it as the control strategy for the system. So as you can see, you got an input box here, which is the driver, and he's inputting the alpha, which is the accelerator, and the beta, which is the brake pedal. This goes into a fault detection and fault mitigation block, which is then fed with the control of the accelerator into the brake override system, with a secondary input beta from the brake pedal. This system would try to, in a scenario where the accelerator is at a 20% value and the brake pedal is at, say, 100%, where the person's trying to slam on the brakes, it would prioritize the brake over the accelerator, reduce the accelerator to 0, and allow the driver to stop the vehicle safely. So as you can see, there are many benefits to using model-based simulation for functional safety. It allows you to upfront define ISO 26262 requirements and simulate to make sure you make them and meet the requirements prior to going into the implementation phase, where you're actually having to make all of these requirements on real hardware. You can simulate in software and also come up with fault-tolerant control algorithms to help mitigate or completely mitigate a potential fault or failure of your system. So overall, it's a great methodology for making sure that you're compliant up front with your system and making it easier on the back end for implementing the requirement and checking that box that you comply with the standard. Overall, this research paper was pretty good. I felt like there was a good linear drive into all of the information, where I was able to have no knowledge of this area and dive right in and understand some of the more details of how these systems work and a little bit more understanding of the ISO 26262 standard. They did a good job at simplifying some of the complex algorithms, and even when things seemed a little bit unclear, all of the plots that were provided were a really great way for me to see, okay, I understand now from this plot what they're talking about with some of these algorithms. I didn't discuss the algorithms in detail because this is a 20-minute presentation. If you have interest in learning a little bit more about those control algorithms, the paper is on our Edge site under the files, and you can see all of the details of the implementation algorithms that are used. So overall, I hope you guys learned a little bit about model-based design, and thank you very much for your time.